Now we shall discuss about Rolle's theorem. It is also called as fundamental mean value theorem. It is also called as fundamental mean value theorem because using this mean value theorem further we shall derive the mean values theorem, what are called Lagrange's mean value theorem, Cauchy's mean value theorem, and also Taylor's mean value theorem. So it is fundamental or basic mean value theorem which is used in further discussions. So if you understand only the statement of Rolle's theorem, you can derive Lagrange's theorem as well as Cauchy's mean value theorem as well as Taylor's mean value theorem using the statement of the Rolle's theorem. So let us discuss what is the statement of the Rolle's theorem. What it says, if fx is a real valued function of the real variable x in the closed interval ab such that the first condition fx must be continuous for every x in the closed interval ab, second condition fx must be differentiable in the open interval ab, and the third condition is f of a must equals to f of b. So these are the three conditions for the Rolle's theorem. First condition is fx must be continuous in the closed interval ab. Second condition is fx must be differentiable in the open interval ab. And third condition is the value of the function at the endpoints a and b. The value of the function at the endpoints a and b, that is f of a, must equals to f of b. The values must be equal at the endpoints of the closed interval ab. The conclusion of the theorem says that then there exists at least one point. Then there exists at least one point c in the open interval ab such that f dash of c is equal to 0. F dash of c is equal to 0. So the statement, I repeat once again, fx must be a real valued function defined on the closed interval ab such that fx must be continuous in the closed interval ab, differentiable in the open interval ab, and the third condition is f of a must equals to f of b. Then the conclusion says that there exists a point c such that f dash of c is equal to 0. Of course there may be more than one point, that is what we say, at least one point c such that f dash of c is equal to 0. Now let us consider the proof of the Rolle's theorem. For the proof of the Rolle's theorem, we use properties of continuous functions defined on the closed interval ab. In our previous semester, we have already discussed about the properties of continuous functions defined on the closed interval ab. And the very significant result is when fx is defined on the closed interval ab and continuous on the closed interval ab, the maximum value or the minimum value, what we call extreme value, exists in the interval. That means fx is continuous. When fx is continuous in the closed interval ab, it is bounded, that is the upper bound and the lower bound exists, and it attains its bounds. That is both the maximum value or what we call least upper bound of fx and minimum value, that is called as greatest lower bound of fx, must exist, and there are some points in the interval such that fx has maximum value or minimum value at those points. So we use this property. So it is given that from the first condition fx is continuous in the closed interval ab, so fx must be bounded and it must attain its bounds. That is there must exist some points C and D such that f of C is equal to a maximum value and f of D is equal to minimum value. So then there may arise two cases. In the first case, both the maximum value and minimum value may be same. When fx is defined on the closed interval AB, the maximum value of fx, let it be denoted by big M, and the minimum value of fx, let it be denoted by small m, both may be same. That is, big M is equal to small m. In that case, fx reduces to a constant. Here I have taken the lower value or the minimum value of fx as big L and the maximum value of fx as big M. So when both these coincides, that is the minimum value and maximum value of fx coincides, then there is no variation of fx in the closed interval AB, and hence fx represents a constant value. Fx becomes constant. In that case, its derivative is also 0. F dash x is 0. So f dash of c is 0 where c lies between a and b. So in this case, where the maximum value is equal to minimum value, Rolle's theorem is satisfied. Now let us take the second case where both the maximum value and minimum value are distinct. That means fx has variations in the closed interval AB. You know that fx is continuous in the closed interval AB. It is bounded and attains its bounds. And now there is a variation in fx. That is, the maximum value and minimum value are distinct. It is given that by the third condition, f of a is equal to f of b. So at least one of these values, that is minimum value or maximum value, one value must be distinct from this common value of f of a and f of b. Either the maximum value may be distinct from f of a and f of b, or the minimum value may be distinct from f of a and f of b. So let us take the maximum value big M is not equals to f of a. The maximum value big M is not equals to f of a. What is given in the first condition? Fx is continuous in the closed interval AB, so it must be bounded and it attains its bounds. And here big M is the maximum value of fx and it must be attained by fx in the interval AB, in the closed interval AB. That means there exists some point C such that f of c is equal to maximum value of fx, that is big M. But you know that M is distinct from f of a. That means M is also distinct from f of b. So f of c is also not equals to either f of a or f of b. That means c is not equals to a or b. C is not equals to a or b. That means c lies between a and b. So what is we note here? There exists at least one point C between a and b such that f of c is equal to the maximum value of the function fx. That is, f of c is equal to m. Now we show that the first derivative at this point is 0. That is, f dash of c is equal to 0. We need to show that one. So by the second condition, as fx is derivable in the open interval AB, fx is differentiable at every point between a and b. In particular, fx is differentiable at c, where c lies between a and b. That means f dash of c exists. F dash of c exists. Now consider the right hand derivative of fx at c. The right hand derivative we denoted by r in bracket f dash of c. This is equals to limit x tending to c plus f of x minus f of c divided by x minus c. Of course, this is nothing but the limit of fx minus f of c divided by x minus c, where x tends to c from values greater than c. That is, x is greater than c in this case. So naturally x minus c is positive. X minus c is positive. But f of c is the maximum value. So the numerator fx minus f of c is less than 0. So what we have? Fx minus f of c is less than 0 and the denominator x minus c is greater than 0. So as x tends to c, fx minus f of c divided by x minus c must be less than or equals to 0. Either it may be negative or 0. That is what we write, less than or equals to 0. So the right hand derivative is less than or equals to 0. And now consider the left hand derivative at x is equal to c. Left hand derivative of fx at x is equal to c. That means here x tends to c from values of x less than c. From values of x less than c. That is, x minus c is naturally less than 0. X minus c is naturally less than 0. But f of c is the maximum value here also. F of c is the maximum value for all x in the closed interval a b. So again f of x minus f of c is less than 0. So in case of left hand derivative, limit x tending to c minus fx minus f of c divided by x minus c, both the numerator fx minus f of c and denominator x minus c both are negative. So the ratio may be greater than or equals to 0. So L of f dash of c is greater than or equals to 0. So we have the right hand derivative is less than or equals to 0 at x is equal to c, and the left hand derivative is greater than or equals to 0 at x is equal to c. But what is required? F dash of c exists, so it must be unique. It must be unique. In other words, both these less than or equals to 0 and greater than or equals to 0 must be happen simultaneously, and this is possible only when f dash of c is equal to 0. F dash of c is equal to 0. That is, the left hand derivative as well as the right hand derivative is equal to 0, and we have f dash of c is equal to 0. Thus we see that the derivative of fx at x is equal to c is 0 or vanish. F dash of c is equal to 0. Similarly, when the minimum value of the function fx in the closed interval a b is not equals to the common value f of a and f of b, then also the above argument can be applied, and we can see that again there exists a point d in the open interval a b such that f of d is equal to the minimum value big L and f dash of d is equal to 0. So the Rolle's theorem here also holds. So what is important here? You may note the conditions of Rolle's theorem. The first one is fx must be continuous in the closed interval a b. Second condition is fx is differentiable in the open interval a b. And the third condition is f of a is equal to f of b. Then the conclusion says that there exists at least one point c in the open interval a b such that f dash of c is equal to 0. So this completes the Rolle's theorem and its proof. And we may note that from this one, at the local maximum and minimum value of fx, f dash x vanishes.